Tonight, we are going to drift gently toward the nearest star system beyond our own, Alpha Centauri. We will not rush there. We will let the distance open slowly from the familiar warmth of Earth, past the quiet orbit of the Moon, beyond Mars, Jupiter, Neptune, and the soft outer edge of the Sun's influence. Then we will look ahead to a faint point of light in the southern sky. It seems close in astronomy books, just a neighbor on a cosmic map, but the more carefully we measure it, the more we understand how deep the space between stars really is. Alpha Centauri is often spoken of as one star, but it is actually a small family of three. Alpha Centauri A is a star much like our Sun, bright and steady. Alpha Centauri B is a little smaller and cooler, circling Alpha Centauri A in a long gravitational dance. Farther out, moving around both of them on a vast orbit, is Proxima Centauri, a dim red dwarf. Proxima is the closest of the three to us, about 25 light-years away, and that makes it the nearest known star beyond the Sun. A light-year sounds like a unit of time, but it is really a unit of distance. It is how far light travels in 1 year, moving at about 186,000 miles every second. Light can circle Earth more than 7 times in 1 second. It can cross the distance from Earth to the Moon in a little over a second. And yet, even at that speed, light from Proxima Centauri needs more than 4 years to reach us. When we look in that direction, we are not seeing the star as it is tonight, but as it was several years ago. That gentle fact changes the feeling of the journey. Alpha Centauri is not simply far away in space. It is also separated from us by time. Any message sent from Earth would spend more than 4 years crossing the dark. Any answer would take more than 4 years to return. A simple exchange, hello from Earth and hello back, would take almost 9 years. This is the first quiet lesson of interstellar travel. Beyond the solar system, distance becomes a kind of silence. In the sky, Alpha Centauri A and B are visible together from the southern hemisphere as a bright point. They seem still, peaceful, and almost close enough to imagine visiting. Proxima Centauri is too faint for the unaided eye, a small red star that must be found with telescopes. It gives off only a fraction of the Sun's light, but it became the center of human attention because it has at least one known planet, Proxima Centauri B, a world only a little larger in mass than Earth, circling its star every 11.2 days. Proxima B is often described as being in the habitable zone. That phrase can sound more certain than it really is. The habitable zone only means that, with the right atmosphere, surface temperatures might allow liquid water. It does not mean the planet is gentle. It does not mean it has oceans. It does not mean it has air we could breathe. It is more like saying the planet is in the right broad neighborhood, not that the house is built, warm, and waiting. Proxima Centauri is a red dwarf, and red dwarfs can be restless stars. They are smaller and cooler than the Sun, so any planet warm enough for liquid water must orbit very close. Proxima B orbits much closer to its star than Mercury orbits the Sun. At that distance, the planet may be tidally locked, with one side always facing the star and one side always turned toward darkness. A world like that would have no ordinary days or nights. It would have a permanent dawn line, a border between light and shadow. There is another difficulty. Proxima Centauri produces strong flares, sudden bursts of ultraviolet light and charged particles. These flares could wear away an atmosphere over long periods of time, especially on a planet orbiting so close. If Proxima B has a thick atmosphere, it may carry heat from the bright side to the dark side. If it lost its atmosphere, it may be a quiet rock under a red and changeable star. From Earth, with present instruments, we still do not know which version is true. The larger Alpha Centauri pair is also intriguing. Alpha Centauri A and B are more Sun-like, and in recent years astronomers have searched carefully around them for planets. In 2025, observations with the James Webb Space Telescope found strong evidence for a possible giant planet around Alpha Centauri A. If confirmed, It would not be a second Earth because it appears to be more like a gas giant, but it would still be an astonishing discovery. The nearest sun-like star may have its own planetary companion, so the destination is not a single dot. It is a small, complicated neighborhood, 3 stars, at least one confirmed planet around Proxima, possible worlds around the brighter pair, and many unanswered questions. It is close enough that it has become the natural first target in our imagination. And yet, close in astronomy is not close in human terms. The same distance that makes Alpha Centauri our nearest stellar neighbor also makes it almost unreachable with the machines we have built so far. If we could somehow float above the solar system and look back, Earth would be a blue speck near one ordinary star. The planets would be small beads moving through darkness. Far beyond them, Proxima Centauri would still be invisible to our eyes. Not because it is absent, but because the gulf is so large. That gulf is not empty in the poetic sense. It contains thin gas, dust, magnetic fields, cosmic rays, and silence. But compared with the worlds we know, it is emptiness on a scale the human mind has to approach slowly. Even the word nearest can be misleading. In ordinary life, nearest means easy, reachable, familiar. The nearest chair, the nearest door, the nearest town. In astronomy, nearest can mean a place so far that human language has to stretch to describe it. Alpha Centauri is near only because everything else is farther. It is close the way a mountain peak across an ocean might be close compared with the moon. The comparison is true, but it does not make the voyage small. That is why this story can be both calming and unsettling at once. We are not imagining monsters in space. We are imagining scale. The calm comes from the steady laws of nature, from gravity, light, motion, and time. The unease comes from realizing that those laws leave very wide spaces between the places where warmth and life gather. Alpha Centauri waits in the nearest of those wide spaces, a first marker on a map that is almost entirely dark. For tonight's journey, we will imagine what it would truly mean to cross that gulf. We will begin with the distance itself, then the speeds required, then the engines people have dreamed of, from nuclear pulses to sails of light. We will think about the ship, the crew, the decades of routine, the hazards hidden in apparently empty space, and the strange arrival at another sun. You do not need to hold every number in your mind. Let them pass like stars outside a window as we drift toward the nearest star. To understand the journey to Alpha Centauri, it helps to begin with a familiar kind of motion. A passenger jet crosses an ocean in hours. A spacecraft crosses the distance to the moon in days. Mars missions take months. Jupiter requires years. These are already long journeys for human planning, but they are still journeys within the sun's family. The distances are large, but they belong to one neighborhood. Alpha Centauri is different. It is not the next house on the street. It is the next village across an almost unimaginable desert. The distance to Proxima Centauri is about 25 trillion miles. Written out, that number becomes heavy and nearly meaningless. 25 trillion is 25,000 billion miles. If every mile were a heartbeat, the counting would go on for hundreds of thousands of years. If Earth and the Sun were reduced to a comfortable scale, with Earth a small bead orbiting a lamp across the room, Alpha Centauri would not be in the next room. It would be miles away, another lamp shining from far beyond the horizon. Our fastest spacecraft gives us a useful comparison. NASA's Parker Solar Probe, diving close to the Sun, reaches about 430,000 miles per hour at closest approach. That is faster than any human-made object has ever moved. It is so fast that it could cross the continental United States in seconds. But if that speed could somehow be aimed straight toward Proxima Centauri, the trip would still take roughly 6,000 to 7,000 years. Human history from the first cities to today is shorter than that. Voyager 1, which has crossed beyond the heliosphere into interstellar space, is much slower than Parker Solar Probe. It is an extraordinary machine, but its path through the galaxy is not a road to another star in any human time frame. It will pass relatively near other stars only after tens of thousands of years, and even then, near means more than a light year away. This is the second quiet lesson. Leaving the solar system is not the same as reaching another star. To make the journey in a human lifetime, the spacecraft would need to move at a meaningful fraction of the speed of light. At 1% of light speed, Proxima Centauri would still be more than 400 years away. At 10% of light speed, the travel time drops to about 42 or 43 years, ignoring acceleration and braking. That is the kind of speed that begins to fit within a human life. But it is also a speed far beyond any large spacecraft we know how to build. 10% of light speed is about 67 million miles per hour. It is not merely faster than our spacecraft. It is a different category of motion. At such speeds, the energy stored in the moving ship is enormous. The ship is not gliding gently through space in the everyday sense. It is carrying the kinetic energy of a civilization-scale project. Even a small object moving that quickly becomes dangerous. A grain of dust is no longer a grain of dust. It becomes an impact event. Acceleration matters as much as speed. A human crew cannot simply be snapped instantly to 10% of light speed. If the acceleration is too high, bodies and structures fail. If the acceleration is comfortable, perhaps one Earth gravity, the ship would spend weeks or months building speed. Then, at the far end, it would have to slow down again. Braking requires energy too. In space, there is no road friction, no atmosphere, no gentle coast to a stop. Every mile per second gained must somehow be paid for again if you want to arrive, not merely pass by. This is where the rocket equation enters the story. A rocket must carry the fuel it uses to accelerate, but fuel has mass, and mass requires more fuel to move. Add fuel to go faster, and you need still more fuel to push the added fuel. The equation grows harsh very quickly. Chemical rockets are wonderful for climbing away from Earth and traveling between planets, but they are not suited for starflight. The amount of propellant required becomes absurd long before the destination becomes reachable. There are ways to soften the rocket equation. You can use more efficient engines. You can use energy beamed from elsewhere, so the spacecraft does not carry all its power. You can make the payload very small, perhaps a robotic probe no larger than a chip. You can accept a flyby instead of stopping. Each solution removes one burden and introduces another. The journey to Alpha Centauri is not blocked by one wall. It is blocked by many walls arranged one behind the other. Relativity also begins to whisper at these speeds. At 10% of light speed, time dilation is small, but real. The crew would experience a little less time than observers on Earth. At higher speeds, this difference grows. A spacecraft traveling near light speed could, from the crew's point of view, make the journey in less time than Earth would measure. But the energy needed to approach such speeds rises dramatically. The closer you get to light speed, the more difficult each additional increase becomes. Communication keeps the journey tied to Earth, but loosely. At first, messages might feel almost ordinary, delayed by minutes or hours. Then the delay becomes days, then months, then years. By the halfway point, a message home and an answer back could take more than 4 years. The crew would not be asking for instructions. They would be sending letters into the past and receiving letters from a world that had already changed. The farther they went, the more independence would become not a preference, but a necessity. A helpful way to feel the distance is to think about speed as a kind of language. Walking speed belongs to the body. Car speed belongs to cities and highways. Jet speed belongs to continents. Rocket speed belongs to planets. But star speed is another language entirely. To speak it, a machine must move so quickly that ordinary ideas of travel begin to fade. At interstellar speed, a journey is not a route, it is an era. Even a small improvement in travel time changes the human meaning of the mission. 6,000 years is archaeology. 400 years is a civilization. 40 years is a career, a marriage, a childhood becoming adulthood. At 10% of light speed, Alpha Centauri enters the edge of human experience, but only just. It becomes possible to imagine a person leaving and arriving, but not returning unchanged. The numbers become biographies. So before we imagine engines, habitats, or landing on a distant planet, the distance itself has already shaped the entire mission. It demands extreme speed. Extreme speed demands enormous energy. Enormous energy demands technology beyond what we routinely possess. And the time required changes the mission from a trip into a life. A journey to Alpha Centauri would not be an expedition measured in days like Apollo, or months like Mars. It would be a long human season, a life lived between two stars. Once the distance is understood, the next question is simple and difficult. What could possibly push a spacecraft that far? Chemical rockets are familiar, powerful, and proven. They lift satellites, astronauts, and planetary probes. They turn stored chemical energy into hot gas and thrust, but their energy density is too low for interstellar travel. They are like strong legs at the bottom of a mountain range that extends all the way to the clouds. They can begin the climb, but they cannot carry us across the full distance between stars. Nuclear thermal rockets would be a step beyond chemical rockets. Instead of burning fuel with oxygen, a reactor would heat a propellant such as hydrogen and send it out through a nozzle. This could be more efficient than chemical propulsion, and it may be useful for travel within the solar system. But even this does not solve the Alpha Centauri problem. It improves the engine, but not enough. The difference between reaching Mars faster and reaching another star is so large that a modest improvement is still swallowed by the distance. Nuclear pulse propulsion is more dramatic. In the mid-20th century, engineers studied the idea of throwing small nuclear explosives behind a spacecraft and riding the repeated push from the blasts. It sounds like something from a fever dream, but the physics was taken seriously. A massive shock plate would absorb each explosion, and the ship would lurch forward, pulse after pulse. In theory, a large nuclear pulse craft might reach several % of light speed. In practice, the engineering, radiation, treaty issues, and political reality make it deeply difficult. Fusion propulsion is gentler to imagine, even if it remains extremely hard to build. Fusion is the process that powers the sun, combining light atomic nuclei into heavier ones and releasing energy. A fusion engine could, in principle, provide far more energy per kilogram of fuel than chemical rockets. It might use isotopes of hydrogen and create an exhaust moving incredibly fast. But controlled fusion on Earth is still a developing technology. Building a compact, reliable fusion rocket that works for decades in deep space is a challenge beyond our present reach. Antimatter is the most efficient fuel physics allows. When matter meets antimatter, both can convert almost completely into energy. In equations, it is beautiful. In engineering, it is almost impossibly delicate. We can create tiny amounts of antimatter in laboratories, but not remotely enough to fuel an interstellar ship. Storing it would require perfect containment, because if antimatter touched ordinary matter, it would release its energy at once. An antimatter starship is a powerful idea, but for now it belongs near the far edge of speculation. Electric propulsion, such as ion drives, is real and graceful. These engines accelerate charged particles with electric fields, producing very efficient thrust. The thrust is small, but it can continue for a long time. Ion drives have already carried robotic spacecraft through the solar system. For interstellar travel, though, the problem is scale. To push a large crewed ship to a meaningful fraction of light speed, the power requirements become enormous. An ion engine is patient, but Alpha Centauri demands not only patience, but extraordinary power. Then there are sails. A sail does not carry all its own propellant. It uses light. Photons have momentum, and when they reflect from a shiny surface, they push. The push is tiny, almost too small to feel, but in space a tiny push can accumulate. A solar sail can slowly gain speed from sunlight. The difficulty is that sunlight fades with distance. Beyond the inner solar system, the push weakens. A sail bound for another star would need a stronger beam than the sun can provide at large distances. This is the idea behind laser sails. Instead of waiting for sunlight, a powerful laser array near Earth would focus light onto a reflective sail, pushing it rapidly. The breakthrough starshot concept imagines very small, light-driven nanocraft accelerated to a significant fraction of light speed, potentially reaching Alpha Centauri in just over 20 years. The craft would be tiny, perhaps gram scale, more like a flying instrument than a ship. It would not carry people. It might take pictures, gather a little data, and send faint signals home. Laser sail missions are among the most plausible first steps toward Alpha Centauri, but they come with their own quiet problems. The beam must stay focused on a tiny sail as it races away. The sail must survive intense illumination without melting or tearing. The probe must endure interstellar dust impacts. When it reaches the star system, it would not stop. It would fly through at tremendous speed, collecting what it can in hours or days. Then it would continue into the dark, its brief encounter already over. A crewed mission is much harder. People need air, water, food, gravity, shielding, space, medicine, companionship, and time. The ship cannot be a gram-scale chip. It must be a moving habitat, perhaps a small world. The moment humans are included, every problem grows. Mass rises. Power needs rise. Failure becomes morally heavier. A robotic probe can be lost with sadness. A crewed ship carries lives, memories, families, and the weight of a civilization's trust. Some ideas try to avoid the need for extreme speed. A generation ship would travel slowly, perhaps for centuries, with the original crew's descendants arriving at the destination. This lowers the propulsion burden but raises profound human questions. The people who arrive never chose to leave Earth. They would be born inside the mission. Their society would have to remain stable for generations inside a closed environment. The ship would not just be transportation. It would be a nation, a school, a farm, a hospital, and a myth. Every proposed engine carries a philosophy. A nuclear pulse ship says power can be blunt, enormous, and explosive. A fusion drive says the star's own process might someday be folded into a machine. An antimatter engine says mass itself could become motion. If we could learn to hold the most volatile fuel imaginable. A laser sail says perhaps the ship should be light, almost weightless, letting energy remain at home while a small messenger rides a beam into the dark. It may be that the first true interstellar mission will not look like a ship at all. It may be a collection of tiny craft, sent in numbers because some will be lost. They would not carry the drama of a crew looking through windows. They would carry instruments, memory, and a slender radio voice. Their courage would be borrowed from their makers. If they succeed, the first close visitor to another star may weigh less than a coin. Another possibility is suspended animation, or some future form of hibernation, allowing travelers to sleep through most of the voyage. It is common in science fiction, but not presently available for humans. Even if someday possible, it would introduce new risks. Bodies would need to survive decades in a controlled state. Machines would have to monitor them without failure. Waking would have to be reliable. The dream is calming. A ship of sleepers moving between stars, but the science is not ready. For now, the engines remain dreams, partial answers, and patient sketches. If a crew ever sets out for Alpha Centauri, the spacecraft will have to become more than a vehicle. It will be the crew's home, landscape, weather, workplace, and community. There will be no outside air, no natural rain, no open sea, no quiet forest path. Every breath will be made by machinery and biology working together. Every drop of water will be cleaned and returned. Every meal will come from stores, gardens, or carefully managed growing systems. The ship will need to carry a small version of Earth inside it. Water recycling would be one of the central systems. On the International Space Station, water is already recovered from humidity, urine, and other sources, then purified for reuse. A starship would need even higher reliability and efficiency, because small losses add up across decades. A leak that seems minor on Earth could become serious in interstellar space. The crew would think about water differently. It would not simply come from a tap, it would be part of a loop, passing through bodies, filters, plants, tanks, and back again. Food would be a living project. Carrying all the food for a multi-decade voyage would be heavy and limiting. Growing food on board would provide nourishment, oxygen support, and perhaps emotional comfort. Imagine long rooms lit by soft artificial sunlight, rows of leafy greens, dwarf wheat, potatoes, beans, herbs, maybe fruit trees bred to stay small. These gardens would be practical, but also psychological. A green leaf in deep space might become one of the most important sights on the ship, a reminder that Earth is not entirely gone. Air would also need to circulate through living and mechanical systems. Carbon dioxide would have to be removed or fed to plants. Oxygen would need to be replenished. Trace contaminants would be filtered. The smell of the ship would become part of life. Metal, plastic, warm electronics, damp growth chambers, recycled air, perhaps the faint scent of soil substitutes and leaves. People might long for the messy variety of Earth, ocean salt, wet pavement, pine forests, cooking smoke, flowers after rain. On the ship, the air would be clean, but familiar in a way that might become heavy. Gravity is another quiet necessity. Humans can live in weightlessness for months, but decades would damage bones, muscles, circulation, and vision. A crude Alpha Centauri ship would probably need artificial gravity, most likely through rotation. A rotating ring or cylinder could press people gently outward, creating a feeling like weight. The larger the radius, the more comfortable the spin. Too small a ring, and the inner ear may feel the rotation. Too large, and the structure becomes more massive and difficult to build. Even gravity becomes an engineering compromise. A rotating habitat would shape daily life. Floors would curve very slightly. Looking far enough down a corridor, you might sense the geometry of the world bending around. The sky would be the ceiling, lights arranged to mimic morning and evening. Sleep cycles might be tuned carefully, not just for comfort, but for mental health. Without sunrise, sunset, seasons, or weather, time would need to be created. The ship would have calendars, rituals, work shifts, quiet hours, celebrations, and perhaps a simulated night when lights dim and the machinery hums more softly. Medical care would have to be broad and self-sufficient. A doctor on board would not be enough. The ship would need equipment for surgery, dentistry, imaging, infection control, childbirth if permitted, mental health care, rehabilitation, and end-of-life care. Supplies would age. Medicines can degrade. Instruments can fail. The crew would need the ability to manufacture some replacements, perhaps with advanced printers, chemical synthesis, and stored biological cultures. On Earth, a hospital is part of a network. On the starship, the hospital is alone. The emotional life of the crew may be the most delicate system of all. Machines can be tested. Human communities cannot be perfectly predicted. People in isolation form friendships, loyalties, frustrations, romances, griefs, and rivalries. A joke repeated for 10 years can become unbearable. A small conflict can harden if there is nowhere to cool off. The crew would need privacy, counseling, conflict resolution, shared purpose, and enough meaningful work to keep life from narrowing into mere waiting. There would also need to be governance. Who makes decisions when Earth is years away? What happens if the commander becomes ill, or if the crew loses faith in leadership? What counts as a crime on a ship where exile is impossible and imprisonment wastes precious space and care? These questions sound political, but on a starship they become as practical as oxygen. A peaceful mission requires rules, and those rules must be trusted long before they are needed. Communication with Earth would become a slow thread connecting two worlds. At first, the crew might receive news, music, messages from family, scientific updates, and ordinary human chatter. Later, the delay would stretch. Births, deaths, elections, disasters, jokes, fashions, discoveries, all would arrive late. The crew would watch Earth change from a distance, unable to participate in the same rhythm. They would become an offshoot of human history, still connected but moving through a different kind of time. Children, if any were born during the journey, would make the mission deeper and more difficult. A child born aboard would not remember Earth. Their earliest world would be corridors, gardens under lamps, rotating floors, and stories of a blue planet they had never touched. Their education would be practical and philosophical. They would learn mathematics and maintenance, but also what oceans are, what wind feels like, why birds mattered to the people who left. For them, Alpha Centauri might not be a destination. It might simply be the place adults promised would come someday. Privacy would become a precious resource. On Earth, loneliness and solitude are different things, and we can usually choose between them. On a ship, solitude must be designed. Small cabins, quiet rooms, darkened observation spaces, perhaps virtual forests or oceans, all would help people feel that their inner lives still have room. The crew would need each other deeply, but they would also need moments when no one asked anything of them. Memory would need caretakers. A journey lasting decades can blur its beginning. Videos of Earth, recordings of waves, languages, family histories, regional songs, recipes, jokes, and photographs would become part of the ship's emotional infrastructure. They might be stored in archives, taught in schools, performed on anniversaries. The mission would not simply transport bodies to Alpha Centauri. It would transport culture, and culture is fragile unless people keep choosing to remember. In this way, the ship becomes the true heart of the journey. Alpha Centauri is the goal, but the decades between may define the travelers more than the arrival. The mission would be a long experiment in keeping a small world alive. It would ask whether people can carry not just technology, but kindness, patience, memory, and meaning across interstellar distance. A successful ship would need strong engines, but also soft spaces, gentle routines, resilient friendships, and the wisdom to make a home in the dark. Interstellar space looks empty, and compared with a planet or an atmosphere, it is. But for a spacecraft moving at a fraction of light speed, even tiny things matter. A dust grain drifting quietly between the stars becomes dangerous when the ship meets it at tens of millions of miles per hour. The energy of an impact rises with speed. A small particle that would be harmless at ordinary orbital speeds can become a bullet of plasma, heat, and shock at interstellar speeds. The darkness ahead must be treated like weather. A crewed ship would need a shield at the front, possibly many layers. There might be a thick physical shield, a cloud of sacrificial particles released ahead of the craft, or a system designed to vaporize incoming dust before it reaches the hull. Magnetic fields could help deflect charged particles, though not neutral dust. Radar or laser detection might warn of larger objects, but at high speed there is little time to turn. The safest protection may be redundancy, many layers designed to fail gracefully, one after another, instead of all at once. Radiation is quieter than impact, but always present. Beyond Earth's atmosphere and magnetic field, cosmic rays arrive from across the galaxy. They are high-energy particles, some born in supernova shocks and other violent places. Over years, they can damage electronics and living tissue. A spacecraft carrying people would need shielding, perhaps water tanks, fuel, and supplies arranged around crew areas. But heavy shielding adds mass, and mass makes acceleration harder. Again, the mission becomes a balance between protection and possibility. The ship's electronics would have to survive for decades. Radiation can flip bits in memory, degrade sensors, and slowly damage materials. Computers would need redundancy, error correction, shielding, and the ability to repair or replace parts. The crew might spend much of the journey not exploring in a glamorous sense, but maintaining systems, checking seals, replacing modules, cleaning filters, recalibrating instruments, inspecting the hull, and listening for small changes in the machinery. On an interstellar ship, maintenance is survival. Navigation is another hidden challenge. Alpha Centauri is moving. The sun is moving. The spacecraft is moving. The target seen from Earth is not where it will be when the ship arrives. Mission planners must aim not at the star's present position in our sky, but at its future position decades later. During the voyage, the ship would use star trackers, pulsars, onboard clocks, inertial systems, and repeated observations to refine its path. A tiny error at launch can grow into millions of miles of missed distance after light years of travel. At high speed, even the view of the stars changes. The stars ahead shift slightly toward blue. The stars behind shift toward red. The pattern of the sky compresses in the forward direction. These effects are mild at 10% of light speed, but still important for precise navigation. The crew would not be flying through the familiar sky of Earth. They would be moving through a subtly transformed star field, one that reminds them with every measurement that they are no longer still. Then comes the problem of arrival. Reaching Alpha Centauri is not the same as stopping there. A flyby probe can rush past, collect data, and continue. A crewed ship must slow down. Deceleration requires as much seriousness as acceleration. The ship might carry fuel for braking, use a magnetic sail to interact with stellar wind, deploy a light sail, or combine several methods. Each option depends on the environment near the destination and the mass of the ship. Stopping may be the hardest part of going. If the ship approaches Proxima Centauri, the first close view would be unlike the Sun. Proxima is small and red, glowing with a dimmer, cooler light. Proxima b, if it has an atmosphere, might show phases, clouds, or a glint of liquid on its surface. If it is bare, it may look stark, cratered, and silent. Because it orbits so close, the planet may keep one face toward the star. The day side could be bright and harsh, the night side cold and dark, with any more temperate region near the terminator. The flares of Proxima would matter greatly. A planet in the habitable zone of a red dwarf can receive intense bursts of ultraviolet and X-ray radiation. If it has a strong magnetic field and thick atmosphere, those might provide protection. If not, the surface could be hostile to complex life. Life, if it existed, might shelter underground, underwater, or under ice. From orbit, the crew would search for atmospheric gases, surface patterns, seasonal changes, chemistry, and any hint that biology had touched the planet. The brighter Alpha Centauri A and B might offer a different kind of interest. They are more sun-like, warmer and steadier than Proxima. A confirmed planet around Alpha Centauri A, especially a giant planet, would teach us about how planets form in binary star systems. Even if not habitable, such a world could have moons or complex orbital relationships. The Alpha Centauri system is not just one possible destination. It is a natural laboratory, close enough to tempt us and strange enough to humble us. The first human arrival would be filled with uncertainty. The crew might find a promising world, a barren world, or a world that once had water but lost it. They might find no life at all, which would be a profound silence. They might find simple chemistry that hints at biology. They might find an environment too dangerous to enter but too important to ignore. Whatever they found, the news would take years to reach Earth. Humanity would learn the answer slowly, through old light and patient signals. The most difficult hazards may be the ones that happen slowly. A shield weakens over years. A pump becomes less efficient. A crew member's vision changes. A garden crop begins to fail. Stress accumulates quietly. Interstellar travel rewards attention to small things. The dramatic disaster is easy to imagine, but the more realistic danger may be ordinary wear, multiplied by time, in a place where every replacement part must already be aboard or made from what the ship can spare. Arrival would also bring emotional risk. After decades of imagining the destination, the real Alpha Centauri system might not match anyone's hopes. A world may be less blue than expected, less alive, less welcoming. The crew would need to love truth more than fantasy. Exploration is not a promise that the universe will satisfy us. It is a promise that we will look carefully and accept what is there. And if something went wrong near arrival, after decades of travel, there would still be no rescue. A failed braking system, a damaged habitat, a radiation storm, a navigation error. Any of these could threaten the mission at the very moment success seemed close. This is why the journey is both frightening and beautiful. It asks for a kind of courage that is not loud. The courage of careful design, repeated checks, quiet discipline, and trust. A starship does not survive on bravery alone. It survives on patience made into engineering. After all of this, the natural question is why anyone would go. Why send a probe, or someday people, across such a distance? Why spend decades reaching a place that may be barren, dangerous, or unreachable in any practical sense? The answer is not one thing. It is curiosity, survival, beauty, ambition, and the old human habit of looking beyond the nearest hill. Alpha Centauri is the first hill beyond the solar system. It is not easy. It is simply first. Robotic missions may come long before crude ones. A tiny laser sail probe could, if the technology matures, give us humanity's first close look at another star system. Even a few images of Proxima b, even a rough spectrum of its atmosphere, would change the feeling of the night sky. A point of light would become a place. The nearest star would no longer be only a number in a textbook. It would be a landscape, a weather system, a set of measurements gathered by something we made. That may be how interstellar exploration begins, not with a grand arc of people, but with patient, fragile messengers. Small probes sent in fleets, some failing, some surviving, some returning faint data years after their flyby. Each one would be a message from Earth to the dark, and a message from the dark back to Earth. The first results might be modest, a blurred crescent, a temperature estimate, a magnetic field measurement, a few packets of data. But in science, modest facts can open enormous doors. Crude starflight, if it ever happens, may require a different kind of civilization. One that can plan across generations, cooperate across nations, preserve knowledge for long periods, and accept that the people who begin a project may not see its end. Interstellar travel is not just a technology test, it is a maturity test. It asks whether we can think beyond urgency, beyond profit, beyond one lifetime. It asks whether humanity can act with the patience of the stars it hopes to visit. There is also the question of survival. Earth is precious, but it is not permanent. The sun will change over deep time. Asteroids, climate instability, supervolcanoes, artificial risks, and unknown dangers remind us that a species living in one place is fragile. Becoming a multi-planet species would reduce that fragility. Becoming a multi-star species would reduce it even further. Alpha Centauri would not be an escape from caring for Earth. It would be a reminder that life is rare and worth protecting wherever it can take root. Still, we should not imagine the stars as an easy solution to Earth's problems. The journey is too hard, the distance is too vast, the time scales too long. There is no simple evacuation to Alpha Centauri, no quick second home waiting 4 light years away. Any future there will be built slowly, at great cost, by people who carry Earth's lessons with them. If we cannot learn to care for one planet, we may not be ready to care for another. Perhaps the deepest reason to go is not escape, but understanding. To see another star up close is to see our own sun differently. To measure another planet is to understand Earth more fully. To learn whether Proxima b has air, weather, oceans, ice, or nothing at all would help answer how common Earth-like conditions may be. The nearest star system is a mirror held far away. In trying to reach it, we learn about physics, engineering, biology, society, and ourselves. There is a gentle paradox in this. The journey to Alpha Centauri sounds like leaving home, but it may teach us what home means. The farther a spacecraft travels, the smaller Earth becomes, not in value, but in appearance. A blue world, then a pale point, then one star among many. The distance does not make Earth less important. It makes the living surface of Earth seem astonishing. A fragile island of water, air, soil, memory, and voices in a wide sea of night. For a crew on the way, if such a crew ever exists, meaning would come from small things: a shared meal under artificial light, a repaired pump, a message from Earth, already years old, still carrying love, a plant unfolding a new leaf, a child learning the names of oceans they have never seen, a star ahead growing slowly brighter over decades. The mission would not be heroic every day. Most days would be ordinary, and that may be what allows it to continue. For those of us on Earth, Alpha Centauri can remain a calming thought as well as a daring one. It reminds us that the universe is not built on our schedule. Light itself takes years to cross the nearest gap between stars. The stars do not hurry. They burn, orbit, flare, age, and move through the galaxy in long rhythms. To think about Alpha Centauri before sleep is to place our own worries inside a much larger quiet without making them meaningless. Someday, perhaps, a signal will arrive from a tiny probe that has passed through the Alpha Centauri system. Someday later, perhaps, a larger craft will follow. Or perhaps the journey will remain a dream for centuries, shaping our questions more than our maps. Either way, the nearest star has already changed us. It has given us a first destination beyond the sun. It has made the phrase interstellar travel feel not close, but imaginable. There is comfort in knowing that we do not have to solve the whole journey tonight. No single generation has to answer every question. One generation measures the stars. Another builds better telescopes. Another learns to sail on light. Another may send the first probe. Another, much later, may decide whether people should follow. Great journeys often begin as patient layers of work, each one resting on the one before it. So, as your mind settles, Alpha Centauri can become not a threat, but a distant lantern. It shows us how far there is to go, and also how carefully knowledge travels. 4 light years of darkness cannot be crossed by impatience. They require calm, precision, humility, and wonder. Those are gentle qualities. They belong as much to a sleep story as to a starship. And so tonight, as we end this slow journey, we can picture the solar system from far away. The sun behind us, warm and golden. The planets folded into a small family of orbits. Ahead, the faint red glow of Proxima and the brighter pair of Alpha Centauri A and B, waiting in their long dance. Between them and us, more than 4 years of light, and a silence wide enough to hold generations. It is a difficult journey, perhaps the most difficult we can imagine, but it is also a gentle reminder that curiosity can travel farther than fear, and that even the nearest star can teach us how vast and beautiful home really is.